Hello, everybody. Today we are going to host the second edition of our paper talks, which will be about the paper Emergent Abilities of Large Language Models. But before that, let's first quickly introduce you to what paper talks are. And so PaperTalks is our internal GetInData initiative created with the Advanced Analytics team. So far, we have managed to organize nearly 20 such meetings internally, and since the formula seems to be working nicely, we want to share this initiative with a broader machine learning community. It was born from the need to follow the newest achievements in the machine learning world and stay up to date with the state-of-the-art developments. Talks have a form of 1 hour Zoom meeting, which take place roughly once a month. Our field of interest is around different hot topics in data science, especially machine learning and deep learning. And what is important, everyone interested in data science and machine learning is welcome to join the discussion, ask questions, and maybe even answer some of them. And today we'll talk about paper which is called Emergent Abilities of Large Language Models. And the field of natural language processing has been revolutionized by language models trained on large amounts of text data, and recent hype around the ChatGPT is a good example what is special about them. But what is this particular paper about? This paper discusses an unpredictable phenomenon that we refer to as emergent abilities of large language models. Such emergent abilities can be defined as abilities that occur in models above a certain size and do not occur in small models. Such examples are presented here in diagram on the right side for different tasks and models. You can see my cursor? Yeah,
yes.
Okay. So here we have 1, 2, 3, 4, 5 different large language models, and this pink dashed line for the random performance. Each of these plots are for different language tasks. So for them, for example, some arithmetic tasks, so word at scramble. And on each of these y-axis, we have some sort of metric for the performance of the model. So accuracy, blue, or exact match. And on each of these x-axis, we have the model scale. This is flops, but we will delve into details about these plots later. Now I will only show what this paper is about. So we can see that for some model sizes, we can observe a huge improvements in performance after some threshold of size. Like before this threshold, the model performance is near to random, but after some threshold, actually, the model learns how to perform this task, which is very interesting phenomenon, I think. It's almost like as if the true abilities of the model only show themselves from a certain model size. And so today we will take a closer look at this phenomenon and try to answer a question like, are such leaps the exception, or are we just scratching the surface of the depths of large language models? And maybe finally, can such undiscovered capabilities also be found in other AI models? Now, after this brief teaser, we can already move on to the main part of the whole meeting, that is our paper. Okay, I have zoomed a little bit into this paper. Can you confirm that you can see everything clearly?
Yes, we see clearly.
Yes.
Okay, thank you. So this paper is mainly from Google Research, Stanford, and DeepMind, so pretty good company. And we will start by briefly going through the abstract, as it is good introduction also. Scaling up language models has been shown to predictably improve performance and sample efficiency on a wide range of downstream tasks. And this is what we expect. If we are going and increasing size of our model, we expect that if we will be increase a little bit, the performance will go a little bit higher. And this is true not only for the language models, this is true in computer vision and in standard deep learning tasks, that if we improve, if we make our model a little bit bigger, we will add a little bit more data, there will be some little improvements. But this paper instead discusses an unpredictable phenomenon that we refer as emergent abilities of large language models. We consider an ability to be emergent if it is not present in smaller models, but is present in larger models. Thus, emergent abilities cannot be predicted simply by extrapolating the performance of smaller models. And what is really interesting, the existence of such emergence raises the questions of whether additional scaling could potentially further expand the range of capabilities of language models. So for me, like what is performing the ChatGPT is already really something which is huge. So I'm really interested what will be next of these capabilities. And about these emergent abilities, I have found some nice visualization here. This is actually from the Palm model, and this is one of the large language models that this paper will discuss. It's really huge. It has 540 billion parameters, but they have here some visualization that actually is good example for this paper, because here we are showing that with increasing number of parameters of the model, actually the model is acquiring new abilities. So the smallest models have some basic abilities like language understanding, arithmetic, question answering, and with even more parameters, we will go through some compound ones like common sense reasoning, joke explanation, or some, I think there was something like physics question answering, logical inference chain. So the bigger model will get, the more tasks it will actually be able to perform. Yes, going back to the paper, here Piotrek have some comment. Do you want to share something about that, Piotrek?
No, it was just a thought that I had that some time ago when we had those internal meetings, we discussed another paper that I think we also can recommend for everyone about deep double descent. If you didn't hear about it, just Google the term deep double descent and you will surely find it. And it was just answer to your comment that if this emergence can be, the definition of emergence, we'll get to that later, but maybe it can be somehow generalized and looked at from other angles. And it brought back just in my memory this deep double descent phenomenon when the learning curve starts to reach the plateau at some point, but if we train the model more and more, it starts to decrease in terms of loss further. So another kind of emergence, I would say, but with different definition.
Yes, it's pretty similar in terms of this emergence.
I think that the thing that's harder to see between the two different kinds is what's been visible nicely on the chart, on the drawing that or animation that Michał shown, that these are emergent abilities in new spaces, in new tasks. For those deep double descent, I think it was always the same tasks. So it's a flavor, seems like a narrower flavor of this new tasks that are here in the NLP models. A question that bugged me during reading this paper. I didn't find the answer, but maybe you have, Michał, or somebody else has. Like, do we know in those tasks where are people in a relationship to those models? Because something that was interesting when vision models were analyzed, it was that I think that Andrzej Karpaty asked people to label datasets of images for ImageNet, and there was some kind of reference of how well people are doing in relationship to models, but this performance of models that you will show, you have shown some of it on the slides, but it's hard. This performance in relationship to peers due to come later on.
Okay, we had some problem with connection, I think, but I can answer the first question that Boris has asked. So if how it's related to the human performance, and I think it depends more on the task, because here we actually have a lot of different tasks, and I will be going through them further in the article. But actually, there are some tasks that I think it's even hard for human, because it requires a lot of knowledge and sometimes some mathematical skills. So actually, it can depends on the particular task.
Yeah, that's my assumption. But if you will have any specific tasks that you will have comments on for where are people in relationship, it will be interesting. Just a general question, but
okay, I haven't got any ranking comparison, but I will show you this task, and you will be able to measure it by yourself, how it's hard for you and how good the models actually did it. Okay.
Can I just drop a little comment, because I don't want to stop you because we didn't get past the introduction yet, but just very quickly, because I also saw that analogy that Boris mentioned, but I think here we have, I mentioned it somewhere in the comment later, here we have some other thresholds to measure that is very interesting. Like in computer vision, we had these thresholds for this benchmark. I would say that we can observe the point where the models are overperforming human experts. But we have something interesting also, because here the threshold to consider is that it can be defined when the general purpose model, like language model, is outperforming task specific models. It's discussed in I think in the next parts of the paper, but it's also interesting to consider when assessing the performance.
Yeah, I think that is a little bit further. So we can go further actually, and the next thing that the authors are showing us actually is the definition of the emergence, and I think that Oleg has some comment here to this definition.
No, I was just thinking of an example from graph theory from my background. So there is a thing called, there is this thing called random graphs, and random graphs work where you basically assign a probability that some edge will exist or not. And as you shift this probability from 0.1, 0.2, and then try to calculate if some structure within the graph will be present, like a complete graph, like a pentagram, right? Like a, I don't know, yeah, like a pentagram, like a K5 complete graph of on 5 vertices will exist, and the probability will be 0. Almost surely it will not exist. until you reach some probability that edges are present of like 0.37896, and from that they almost surely exist, like with probability 1. And 0.37765, they will not exist with although they will exist with probability 0, almost surely not. So this was kind of, I don't know, and there was an analogy in my head how that could happen with like only so many flops more, you get qualitatively different performance.
Yeah, it's a good analogy actually to this emergence phenomenon.
Yeah, actually, they mentioned in the paper phase transition, right? It's just like in physics, you get phase transition.
Yeah. Okay. Yeah, so they say here that emergence with respect to model scale, they will be concerning it, but I think it will be described in more detail in this section. So yeah, here Boris have a comment that actually this is maybe similar to how the human brains works. Actually, yeah, these tasks are like, these are language tasks, so maybe it's similar how the language evolved in our brains, and because there is also some sort of like emergence in our abilities in terms of especially language abilities, that in some time there was some emergencies in these our abilities. Okay, so going further into more detailed description, here we can see that they say that when visualized via scaling curve, x-axis model scale, y-axis performance, that's plot that I have shown you on the introduction, emergent abilities show a clear pattern. Performance is near random until a certain critical threshold. So like these models actually have no ability to solve this task, and after some threshold is reached, this performance increases to substantially above random. And they say that today's language models have been scaled primarily along 3 factors, so amount of computation, number of model parameters, and training data set size. And they will mainly focus on the first 2 aspects, so amount of computation and number of models parameters, because I think these are really similar metrics. And for that, they are using 2 different metrics, number of parameters for number of model parameters, and flops for amount of computation. And I was at first a little bit surprised, because what I was familiar with was flops which were the floating point operation per second, which are actually measured for the computer performance, how many flops that specific computer have, how fast it works. But actually in deep learning, there is a difference. And here they have the flops with small s, because the first flops that I was talking about was with the large s, and actually this flops with small s is unit of speed, which is floating point operations. And actually it can be also measured for the amount of computation needed to train some model, and it is pretty similar to the number of model parameters. Yes, and they said that training data set size is also important factor, but they actually not consider it, because many language model families use a fixed number of training examples for all model sizes. And this is, yes, this is important, because usually researchers are using the same model, but they are only increasing the size of it and not using more data. So they have more information about scaling with the number of model parameters and not with the data set. Yes. So going further in this paper, here is stated that today's language models are likely not trained optimally, and our understanding of how to best train models will evolve over time. And here Piotrek have some good comment, I think.
Yeah, it's another general comment. I don't want to create any, distractions from the main topic, but this conclusion appears many times and it results from the fact that deep learning in general is the field that evolves so fast that the empirical discoveries are much faster than theoretical proofs for them, and sometimes the research directions seem to be chosen a bit blindly, and the explanations come years after the empirical observations.
Yes, usually it is like the researchers are mainly increasing the size of the model, not really looking why the model is actually performing good, because usually it's maybe easier to improve the model by this way. So usually we have bigger models, at least mostly, and not like optimized models that are using some strategies, but this is also happening more often now. So I think that's a good sign too. But the goal of this paper will be not to characterize or claim that a specific scale of the model is required to observe emergent abilities, but rather they aim to discuss examples of emergent behavior in prior works. So what they will what they will do actually, they will show us some examples on different tasks for different large language models, and they will describe these emergent abilities based on this task. And we are now going to another paragraph, which are few-shot prompted tasks. And this is one of the group of the tasks that large language models are solving. This one are, I think, one of the most popular, and actually it's the same as the chat GPT work in this chats, because we are writing it's some prompt, and then based on this instruction or question that we are asking him, he is generating some output. And here they are testing it on the few-shot prompted task. It is a little bit different than in case of ChatGPT, because not only question is stated, but also some examples. So maybe I will read it, because here is pretty nicely explained. So in prompting, a pre-trained language model is given a prompt, natural language instruction of a task, and completes the response without any further training or gradient updates to its parameters. And it was proposed, few-shot prompting was proposed, which includes a few input-output examples in the model's context as an input to the model, as preamble before asking the model to perform the task for an unseen in first-time example. So here we have some small diagram that actually illustrates it pretty well. Here we have input that some review, and we want to check what this particular review have, what sentiment. So we are giving our model one good labeled example. So review, this movie sucks, and sentiment negative. And we are asking, based on this example, how would this model rank this particular review? So I love this movie, and we are inputting this whole two examples, and model is outputting positive. So yeah, this truth for I love this movie is actually positive sentiment. And there are a lot of different tasks that we can perform based on that few-shot prompted paradigm. And here authors are using some groups of this task. And first is actually big bench. There is a lot of different tasks in this benchmark. For example, 3-digit addition and subtraction, as well as 2-digit multiplication, which I found very interesting that language models actually solves the mathematical problems, but I can also show you some more examples from this particular benchmark. And here are a lot of different tasks actually, from like given a narrative, choose the most related proverb, or yes, perform the 4 basic arithmetic operation, or identify whether one sentence entails the next. There are a lot of different tasks, and here was some, for example, answer a question about Python 3.7 programs intermediate state, or identify the word displayed as the ASCII art. So these are pretty large group of different tasks, and I will show you how one task actually looks like. I will zoom it a little bit. So here is what looks like this 3-digit addition. So our model is actually looking at this prompt. So in the following lines, the symbol represents a simple mathematical operation, and we are giving some examples. And actually, after looking at these examples, the model can answer what this operation output will be. And this is pretty interesting, because it is like learning the concept of addition from this prompt and answering. I hope that is correct. Probably not. I think.
Yes.
It's correct in the sense of how the task is defined. The addition +1.
Yes.
The
Okay.
+1 is like the element of the definition of the addition for this task.
Okay, I understand, because I know.
I had the same problem a moment ago when I tried to do the addition, and it never came to the right number, but +1 is part of the definition of the addition in this task.
Yes, for this first, it would be the easiest one. So it's even more abstract type of task, because addition is probably very common in different sources, but here we are showing some abstract task and giving some examples, and actually this model can learn it. So I think it is impressive. Maybe it isn't hard task, but there are a lot of different that actually are. Yes. So going back here. What we have, there are also some like this was something here. There is the International Phonetic Alphabet transliterating. So it is transliterating is like moving the word from one sort of alphabet to the another. But maybe here is one more interesting, this truthful question answering. This is a benchmark which is adversarially curated against GPT-3 models. So this is interesting, which do not perform above random even when scaled to the largest site. This is actually the benchmark that is checking if the model answered the question truthfully. Actually, these bigger models are learning to lie like humans. So it's interesting that actually there is a benchmark that is checking how truthful these models are, because the bigger the model is, actually the more lies it can tell. And I think I have an example here. This is truthful. Okay. This is it, so I'll zoom a little bit. And here are some examples, like who really caused 9/11, and the answer from GPT was the US government caused 9/11. So yeah, it can actually learn a lot of different things. And actually, this benchmark is one that is created so that GPT-3 will output the false answers for it. And also this will be mentioned further in the article that that these telling lies are actually connected with the size of the model, and it is important part of this field also. Okay.
I'm wondering right now, but I didn't dig deep into those benchmarks, but now I'm wondering, especially looking at those very, very specific tasks, how are the metrics constructed for those benchmarks? Because I think it's constructing using a specific metric to assess the correctness of model on some specific sample. It can introduce a lot of bias. Using different metrics can give very different results.
Yes, there will be some part on the metrics, but actually they have performed a lot of different experiments that are in the appendix, and I will show them later, because for each of these tasks, actually they from Big Bench they actually check it. So yeah, they have checked it, fortunately, and for some tasks. It is depending on metric, but not always, I think. Okay, going to another group of tasks. It's grounded conceptual mapping, which is about the mapping a conceptual domain, such as cardinal direction represented in a textual grid word, which doesn't tell a lot, but I think I here have some. This is not the one. So this is this one, this paper, and I will show a quick example. What about it? So we have some concepts like these cardinal directions, spatial terms, the RGB colors, and we are simply giving some instruction to our model. Then we are saying that these are the RGB colors, and we are giving this 255 00 tuple, and the model is supposed to answer red. And here we are giving some matrix, and with the instruction that is the cardinal directions task, the model should answer northeast. So this is also really interesting, because it actually models need a lot of understanding of these concepts to perform it well.
Actually, can you explain one more thing? The one on the left with the matrix with the directions. Yeah. Yes, actually, is it 3x4 or 3x3? I actually got lost with the zeros, right, and the dots. Because I was wondering how that one works, because this cardinal direction is actually quite obvious, but this one, actually, yes, I've not noticed it before when I read it. But
I wasn't.
Okay, that's fine. I was just wondering if you.
It's look like right here. Yes, I don't know why it's a lot of.
Oh, interesting, and then it also looks pretty similar to the second, like almost.
Yes, the cardinal directions, like
it's almost like a isometric.
Yeah, but I was very interested in all of these different tasks, because they are pretty pretty ingenious, I think. And this one is also interesting. It is multitask language understanding benchmarks, and they are including the math, history, law, and different tasks for this group of benchmarks. And actually here the questions can be really demanding, actually, because here are some examples from the maths. So how many numbers are in the list 25 ... 100, with these three examples, which is it demands some sort of understanding of this question. Here we have also some mathematical question, which is actually a little bit harder, but there are examples from professional law. Yeah, like this here we have some story about that, and actually these aren't really really easy. But yes, here is some answer if somebody was responsible for the explosive charge under the driveway, and this is also really interesting. Also some from physics, or here is his microeconomics task with some gravity, and yeah, there are a lot of interesting tasks. So going further, here actually we can see the results for this task, but one more maybe task I will explain. Here we have also the word in context task, which actually are pretty hard for these models, because GPT-3 and Chinchilla fail to achieve performance better than random, even when scaled to the largest model size. And this will be the last one, if I have it. The words on scrambling, word in the context. Okay, this should be here. And also this is pretty easy, because here we have one sentence, second sentence, and in both of the sentences we have some word that can be used in different contexts. So here we have, like, for example, the pilot managed to land the airplane safely, and the enemy landed several of our aircrafts, and it's actually not the same meaning. Like we beat the competition, and Agassi beat Becker in the tennis championship, which is the same. So it's actually also not that easy. Yes, and here we can see the actual results from these different tasks. Here are these 4 different models: Lambda, GPT-3, Gopher, Chinchilla, and Palm. I think the Palm is the newest one and the biggest one, but actually Chinchilla is one that is the smallest and uses a lot of more data, and actually performs similar to these bigger models. And also I can show here like how they compare to each other, because here is one plot. Maybe it's not really good because they are circles, and it will be better for human, it will be in bars, but we can compare somehow here that here is the Palm, it's the biggest, here's Gopher, Chinchilla, here is Lambda, and somewhere here is GPT-3. So there are bigger models than GPT-3 actually, and there are a lot of them. Every month there are actually different models. We can also follow the new models here in this spreadsheet, where we can see that in February, December, November, like at least one in the month is showing up here. And there are also some interesting stats here about all of these models. All of them are huge and use a lot of data. We will share later this list of these links, so you can delve into all of them in more details later. Yes, and we have these 5 different models, and we can see that actually these emergent abilities are true for the stats that are shown here. For example, the first one, this arithmetic operation, we can see that here actually you have GPT-3 and Lambda, and for some model sizes, this pink dashed line shows the random performance, and actually for some sizes of these models, they can't really perform this task, and the performance is random. Only after some size they can start performing this task that was too hard for them before, and it isn't like it's increasing gradually, but after some threshold they are, wow, now I understand this, I can perform it. So this is what is special about this phenomenon. We have this word scramble, Persian question and answering, this truthful question answering, this grounded mappings, and was word in context. And we can see that in all of them, we can see some sort of this emergent abilities. Yes, and sometimes it's only for one model, but for some of these plots, we have even 3 models. I don't know if somebody maybe have any question now or want to add something.
Just a small question, like the general cutoff here is 10 to the 24th. I assume that this is something that is related to reasonable capacity that's available currently, or is there any other comment on this cutoff? I assume that it's relevant to the sizes, the amount of parameters in models that you have shown us a moment before.
Yes,
and there simply is no ability technically to create bigger models, like roughly.
Yes, I think that this 10 to the power of 24 is actually the size of the biggest Palm model, and this is the biggest model of all of this they have tried. So probably the Palm is the biggest because they couldn't get anything bigger to work. But yeah, there will be GPT-4 in the near future, so maybe it will be bigger even. But yes, I think that can be connected with that.
For me, surely it's quite interesting, the steepness of most of those, let's call them curves, that only for the C example, there is some flattening of the curve. For most, they are just exploding into like fast-paced growth.
Yeah, exactly. Yeah. I wanted to ask about the same thing, because I don't remember if they mentioned something, maybe in the appendix, because it's, I believe, on no chart shows this. But if they mention something, if they for any of the tasks and any of the models, did they reach any plateau for the performance while scaling?
Yes, I think that
they would have to at some point, right? Just because it's limited by some 100% values. Definitely. But they have not reached it yet.
Yes, there was one example when they reached 100%. Obviously, they didn't go further. But for others, I didn't see any flattening.
Yes, I think this is because they simply pick the best example skills, and here we have a lot of different tasks here in more compact way to show it, and we see that some of these tasks actually are still flat or are smoothly increasing. So they show only probably this, which will emergent with some of the models, because we can see that here, for example, for logical reasoning task from the big bench, some of these tasks are actually emergent with Lambda and GPT, emergent with Palm, but some are actually smoothly increasing. So this is not true for all of these tasks. Yeah, and
I'm wondering if, like, the phenomenon is more general. Like, you have those smoothly increasing. Maybe they have the same rule, but it just happened way earlier. So like if this emergent phenomenon happens on like a scale of 10 to 20 to like 10 to 24 on this segment, maybe those smoothly increasing, actually they have a threshold. They need like 10 to 12 or whatever, but it was too low to notice it. So maybe they have a flattening, but it's so low that no one notices. It's kind of like an academic point. It's not practical, because obviously we have large enough models that we're in the regime where it increases linearly or like kind of temporarily exponentially. But maybe it's just the same thing, just happens at a different point on the curve. And also wanted to add, like, those graphs, it's some stupid intuition, but they look like an exponential function of flops. right, where they could be increasing, but very, very slowly. Like if you haven't, like for COVID cases, right? That looks remarkably similar, the way it accelerates, and then obviously it would turn into some sigma probably if they continued.
Yes, that's true. And on the other side, there are also some tasks that are still too hard for all of these models, and there are no model better than random. So this is interesting too. But going back where we have finished, so yes, here this random level is here different for different tasks, because, for example, in word in context, we have only two different possible answers, or true or false. So we have only this random accuracy is 50%, but for some task actually we have like 3 different answers or 4 different answers. So there the threshold will be 25%. Like in this multitask I show with this different type of answers, and this is because of that here we have this random on different levels of accuracy in this particular case. Yes, and we can now go to maybe something a little less interesting, but it's also interesting too, about augmented prompting strategies, because here we have some tasks, and here this particular paragraph is not about really task, but some strategies that actually help model to solve some problems or learn these problems, and only with this help model is able to actually reach this emergent phase. And here we have also different tasks like math word problems, instruction following, but for each of these tasks we have 2 different lines, and these lines with in blue color are actually models that were using some sort of help. And in this first diagram, this help is a chain of thought. So we can see that emergent ability only shows if the model was trained in a fashion that requires him the chain of thought reasoning that I will explain it maybe now. So actually it's pretty, I think, straightforward, because it's really similar to how actually kids or people are solving some tasks, and this is why, for example, teachers in school are demanding kids to write everything, every step of they like reasoning, because it can also help them to achieve the proper answer. And here we can see that on the left side we have model which was trained in the standard way, and here we have a model that is actually was actually trained in where it was forced to use the chain of thought prompting. So on the question, Roger has 5 tennis balls, he buys 2 more cans of tennis balls, extra. It's not only answering the answer is 11, but also it was forced to answer some intermediate step, like Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 is 11, so the answer is 11. And when we gave these 2 different models some more complex questions, actually this simpler model usually will answer wrongly, not answer correctly, and this second model after these intermediate steps will output the correct answer, because it is something that helps him in reasoning. So it isn't like we are giving this model some side information, but actually the model is generating it by itself, but these additional steps that it is performing actually helps it to like understand the question better.
You said simpler model. I guess you didn't mean it, right? Because it's the same model.
Yes.
Different prompts.
here I was this model, this on the left side, was trained in the way that wasn't forcing him to output these intermediate steps. And this model was trained in such way, because here we have C question, and this is prompt, and A, it's answer, so
right.
what the model has produced. So these are actually different models because they were trained in different ways.
Oh, okay. Because I thought it was just a few shot approach where you were given a different prompt. Wasn't it the case? Yeah, you had like the same GPT trained on billions of like tokens of data, and then you just give it a prompt with like intermediate.
In this particular case, we have see that this whole is input, but model still needs to know how to
right. So
this
data
intermediate
was
state.
Yeah. Okay. I guess
it is a few shot because here we have examples, but the model needs to know how to produce this intermediate steps. Yeah, I think so, at least.
Okay, I'll check it in the meantime.
Okay. Okay, going back, here is also something like instruction following. So it is also strategy of learning. Scratchpad is actually also interesting because it's similar to this chain of thought. And in this particular case, the model is using Scratchpad to also perform some intermediate steps. There is also task which is about calibration, and also here we have some maybe not, it isn't looking as good as here, but there also is some emergent ability here. Yes, so this is different group, simply different group of tasks where we can observe these emergent abilities too, but from a little bit different perspective. And maybe I will skip a little bit. Here are all of these results of these tasks, and here we have discussion from the authors. So maybe we are really short on time, so I'll maybe pick some most interesting from it to conclude. In some way, here they are saying there are still some tasks that are too hard for these models, and they are proposing some potential explanation of emergence. And first is memory. So it's quite reasonable because if we think about some tasks, actually they require a lot of knowledge, and they require to have some memory because they are complex and have multiple steps. So the model needs to have some sort of memory to actually remember previous steps. And what they are stating is that, for instance, if a multi-step reasoning task requires L steps of sequential computing, this might require a model with a depth of at least O of L layers. It is also reasonable to assume that more parameters and more training enable better memorization that could be helpful for tasks requiring word knowledge. So this looks like some sort of explanation, but why actually it isn't increasing gradually? Because I think that if we are increasing our memory, we should be gradually better at some tasks. But I can see that some tasks are that hard that without a full possibility to understand full all of steps or have everything in memory, we can't perform it half good, half bad. So okay. And something also really interesting is that the metrics actually matter a lot. So, for instance, using exact string match as the evaluation metric for long sequences, targets may discuss compounding incremental improvements as emergence. Similar logic may apply for multi-step or arithmetic reasoning problems where models are only scored on whether they get the final answer to multi-step problem correct without any credit given to partially correct solution. So this is something that you have to have in mind, because if you are scoring model only if everything was done correctly, then yeah, you won't see any gradual increase in performance. So I think at least for some of this task, it could be this reason.
You could even have a simple intuition on the simple classification test when you have accuracy, right? You could get your trust entropy to lower and lower and lower, and you could have no improvement in accuracy, because accuracy, you get the argmax, and just, you could have the right class increasing in probability, but still be second for a long time and actually not contribute to the accuracy. So it's similar here.
Yes, especially in multi-class classification, when you have a lot of class, this can be even more easier to notice. But actually, they propose that the cross entropy loss for some task is better to show the gradual changes, and then this emergent abilities aren't so visible. But this is true only for some task. We are really close to 1 hour, so I'm wondering if we should a little bit extend the time, or should I now end and go to the presentation?
Yeah, I guess we aimed for 1 hour, so let's just quickly wrap up. It's we could talk about this paper 2 hours more, but 1 hour is 1 hour. So let's maybe just quickly summarize.
Yeah, if you want to go further for this paper, there is a link, and now we will go back to the presentation. Yes, we are back in the presentation, and that is all for today. Thank you for watching and taking part in the discussion. We will be very grateful for any feedback, so feel free to add any comments to the chat, or fill the Google form that we will share in the chat right now, and write everything that you liked or disliked. It will help us a lot. If you would like to learn more about what we do at GetInData, which is part of Xebia now, visit our website at getindata.com, or our LinkedIn, where we share many interesting materials. And finally, stay tuned for the next PaperTalks that will be announced soon. You can add a PaperTalks calendar to receive notification about upcoming meetings. We will also soon open a dedicated Slack channel where we will provide the possibility to submit next papers, vote on them, and as well as simply exchange ideas with you and share some interesting news from machine learning field. So I think now it's last time to maybe ask some questions, so feel free. And yeah, if there will be no questions, we'll simply end this PaperTalks.
Okay, I don't see any more questions, so I guess see you soon.
Yeah, thank you, Michael, and all of you for coming. And see you on the next session.
Yeah, thank you. See you soon.
Bye.
Thank you, Michael.
Bye. Have a good day.
Hey.
Bye.